Your next homework assignment's due a week from today, and you'll notice that this is class 25 out of 30. We are really nearing the end of the semester. So prepare emotionally for a day when you don't get to come and learn about hydraulic engineering. It's going to be hard, but you'll have to find some way to get through it because classes don't start again until August. So we're going to be talking about Chapter 14 today, and the entire lecture actually will be devoted to Chapter 14, and then in class next time we're going to start on Chapter 15. So you'll notice this homework assignment that's due on Tuesday is entirely from Chapter 14, and so you'll know, well, we'll cover all the material that you'll need in order to solve that homework assignment, so you can get an early start on that. I won't be in the office next Monday. I don't have office hours on Monday, so I'm not canceling any office hours, but occasionally people stop by on Monday, and I'm happy to have you stop by, but I won't be there next Monday. So if you want to get an early start on the homework, that may improve your odds of getting help from me if you end up needing it. By gradually varying flow, what we mean is a transition zone where the depth or the velocity, some characteristic of the flow is changing as a function of position. And it can be because of a change in slope, or it can be because of a engineered structure like a gate, a weir, a dam. We'll look at the things that cause gradually varying flow, but there's really uniform flow, which is what we started off talking about, rapidly varying flow, which means hydraulic jumps, and gradually varying flow. Those are, broadly speaking, the three categories of flow when we're talking about changes with respect to position. Either the flow depths can be constant, they can change quickly, or they can change slowly. And what we're going to be talking about in Chapter 14 and beyond is what happens when the flow depths change slowly. And in the coming lectures, I'm going to teach you three methods for finding what is the flow depth some distance upstream or downstream from a certain point. So trying to find what's going to be the depth because of these different features that are causing non-uniform flow. But today's lecture is the foundation for those three methods. It's a method for finding what the slope of the water surface is at a point. And then in the coming lectures, we'll learn how to integrate that slope over some distance, given different challenges that arise when we do that. So gradually varying flow is just anything other than rapidly varying flow or uniform flow. And in reality, in a natural setting, most flow is varying gradually. It's very uncommon for there to be a very long stretch of a natural channel where the slope is constant, the roughness is constant, there's no change in width. If you think about what a river or a stream looks like, there's always changes in direction and depth, and so most of the time a river will be undergoing gradual variation in its flow conditions. Now, what we have to know is that when the depth is changing for a certain flow rate, so does the velocity. And so what's going to complicate matters in the methods that we learn in future lectures is that the velocity is changing, and so when we calculate the velocity head at a point, for example, that's going to be changing right along with depth. And so we're going to have to learn methods for finding the average of flow conditions between two sections. That's sort of the heart of the numerical integration method we'll get to next time. But the assumptions that we're going to make when we tackle gradually varying flow is that we are going to account for energy losses. Remember, we sort of neglected them when it was rapidly varying flow. What we said is that in a rapidly varying flow, like a hydraulic jump, the change in flow depth is so quick that 1 and 2 are close together, so we don't necessarily have to worry about the frictional losses between 2 points that are really close together. But now here in gradually varying flow, the points are not close together at all. They're, in some cases, more than a kilometer apart. And so we're going to definitely have to account for energy loss, and usually it's the boundary friction that is the vast majority of that energy loss. So let's look at some pictures of conditions that can cause gradually varying flow. So let's say you've got uniform flow, and in our book, normal depth has the variable y naught. I sometimes write y sub n for normal depth, and I'm not sure what variable the FE manual is using now, but normal depth is associated with uniform flow, and you can calculate normal depth with what equation? Manning's equation, Peyton-Manning's equation, right? It came to him in a vision one time. He got tackled, hit the ground really hard, and all of a sudden Manning's equation came out of his mouth. So here's the normal depth, and gradually varying flow would be if it's getting deeper because there's some sort of a choke. It could be that there is the broad-crested weir choking flow. Here you can see that a gate has choked the flow, and so since it's getting deeper as the flow depth increases, that's a section of gradually varying flow. Here's another feature, the flow off the edge. It could be like, you could think of this as a cliff. As the water is accelerating, it's getting faster because there's no resistance on the other end of that cliff. As it accelerates, its depth decreases, and so we've got gradually varying flow. Once it goes off the cliff, we say that's rapidly varying flow because it's speeding up in free fall. But we won't handle that case. We'll look at the gradually varying flow. Here's probably the most common one. Just the instance of two slopes matching up. You had a normal depth that was associated with one particular slope that's somewhat steeper than the next one. And so we had a steep slope, a more shallow slope, and each one of them had their own normal depth. Even if the geometry is the same, the width didn't change and the roughness didn't change, all you have to do is change one factor in Manning's equation, and then you're going to have a different normal depth. So we have two different normal depths, each of them associated with their respective slopes. And between those two normal depths, where the uniform flow kicked in, there's a gradual variation that matches the two. There won't be a hydraulic jump because both of these slopes were mild slopes. And a mild slope is one that is less than the critical slope. So there's nothing that would support a hydraulic jump in this transition. And here we see water coming out from underneath a gate. And sometimes when I show water coming out from underneath a gate, I write that there's a hydraulic jump here. But in this depiction, there's no hydraulic jump. And what's the difference? Why is there a hydraulic jump in some of the flow underneath the gate, but in this case, there's no hydraulic jump after the flow under the gate? When does a hydraulic jump form is sort of the clue to that. The other way around. So a hydraulic jump forms when you've got supercritical flow. So here's supercritical, and then it transitions to sub. So that's when a hydraulic jump forms. And one of the times that you can have supercritical flow is that if you have a gate, but the slope was mild. And that's what we saw back in the lab. We had a mild slope, and the flow underneath the gate temporarily made the flow supercritical. But here, we've got supercritical flow, but that's just fine because the slope is steep here. And so you'll notice this looks like it's pretty steep just compared to some of the other slopes. And it's gradually varying flow because here it's supercritical, and then it gets to the normal depth, and it's still supercritical. You can have supercritical flow and it be uniform. There is such a thing as uniform supercritical flow. It's just that here that in between these two sections, it's varying gradually because there's no hydraulic jump. There's no need for a hydraulic jump because it's going from one supercritical flow section to another supercritical flow section. So we only see the jump when there's transition from super to sub. Does that make sense to everybody? Okay. Like I said, there's some assumptions that we have to keep in mind as we are applying the equation, the governing equation that we'll look at today. This governing equation assumes that the channel it's being applied to is prismatic. And what we've defined a prismatic channel as before is it has a regular geometry, that it can be defined by shapes like triangles, rectangles, squares, not irregular, in other words. And so a non-prismatic channel would be a river bottom that looks like that. And so the way that they sort of reconcile that assumption with the reality that natural channels usually are pretty irregular is they'll break it up into sections that are quasi-prismatic. You know, if you break it up into pieces, then this is basically a rectangle and so is that, even though taken as a whole, the channel is non-prismatic. Steady flow means that flow conditions are constant over time. Again, that the flow rate is not increasing or decreasing as a function of time. We're going to assume that the bed slope is relatively small. And the reason why we're assuming that is because we want to be able to say that the flow depth and the vertical depth are approximately equal. And we've looked at this a couple of times where if we had a super steep channel, then there would be a difference between this depth, y, and the vertical depth. But most of the time, even with something as steep as a 10% slope, then the vertical depth and the flow depth are about 0.995 the same. So what we'll say is that we'll assume that we'll apply this only when the bed slope is less than 10%, which is plenty steep. Uniform velocity distribution means that we're going to, once again, just like we did in the hydraulic jump, we're going to assume that the flow velocity is the same as we go down through the water. And that's kind of a weak one, but yeah, especially if we have laminar flow. But laminar flow, which is when we'd see a parabolic distribution most distinctly, is pretty rare. So maybe it's not so bad after all for us to be assuming a uniform velocity distribution. The kinetic energy correction factor will be equal to 1. The parallel streamlines and hydrostatic pressure distribution is talking about that because the variation in flow is gradual, we do assume that if you go down through the water, you can have the hydrostatic equation tell you what the pressure at any depth is. You can't apply that inside of a hydraulic jump. There's simply too much turbulence. But in the sections where the flow is varying gradually, it's okay to say that you've got a hydrostatic pressure distribution as you go down through the water. And then finally, channel roughness is constant, which means that we are limited to applying these methods that I'm going to teach you to sections where if we had concrete, but then it changes to maybe like clay, we would have to go in steps. We would have to do our calculations from 1 to 2 and then from 2 to 3. We wouldn't be able to go directly from 1 to 3 because of the difference in material and the difference in the roughness. And so another one of the assumptions in all three of the gradually varying flow methods is that between two sections where you're trying to find how the flow depth changes, you've got basically the same material on the channel bed. Okay, so we're going to go through not the full derivation, but a couple of important parts of it. And if the book does a good job going through the full derivation of what's called the process equation, but I'll just show you a graphical depiction of what's being considered. If we consider an upstream section and a downstream section, we've got a sloped channel, and you'll notice that the channel slope S0 is indicated, so that's the slope of the bed of the water. I'm sorry, the bed of the channel. But you'll notice SW, the slope of the water surface, is different than the channel slope. And so that's one of our first clues that this is not uniform flow, is if you look, these aren't parallel. There is the depth Y upstream, and then downstream there's the depth Y in blue, and then dy in red. So see, here's the blue component, y, dy in red. So that tells us it's getting deeper downstream, which also means that the velocity has to change. If we had velocity v upstream, then there's going to be v plus dv. And in this case, dv would be negative. You know, the velocity is going to be slowing down if the water depth is increasing. S sub f is once again the slope of the energy grade line, or here it's abbreviated total energy line. And you'll notice that the slope of the energy grade line isn't parallel to either the channel slope or the water slope. So there will be three different equations for slope that we're going to be taking into account when we try and calculate the effects of gradually varying flow. You can see that how steep this slope is, the extra elevation, S naught times dl, where dl is the length between the two sections, S naught is the slope, and so this is basically delta z. S naught dl is the delta z between the downstream channel bed and the upstream channel bed. So this picture is important to consider all the components. And if we start with the definition of specific energy, as we've been using specific energy in the past, we say that it's the depth of flow plus the velocity head. So this term is the velocity head term. And if we also accept the fact that dE dy, and we've gone through this part before, is 1 minus the Froude number squared, then we can substitute in the energy grade line slope for dH dl, and by h what we mean is the delta z, the upstream elevation difference between the channel bed at location 1 and the channel bed at location 2. So that's z. Y is the flow depth, and then the velocity head. So in other words, the total energy. And then the slope of the channel is substituted for dz dl. What we end up with is this governing equation, dy dl, and it says it's the change in the water depth relative to the channel bottom in the direction of flow. And so you take the difference between the channel slope, S naught, and the energy grade line slope, S sub f, divided by 1 minus the Froude number squared. So this is an important equation that everything else is based on. It says it's not necessarily the slope of the water surface, because the slope of the water surface takes into account the channel bed slope and the dy dl. But if you know the channel bed slope, then you can find the slope of the water surface by combining dy dl and the channel bed slope. Okay, so I'm going to make a brief digression and ask you, so this equation tells us how the water depth is changing. So let's say we have a channel like this, and the water depth is changing. And so we can solve this at a point. So let's say that, we analyze the situation and we find out dy dl at this point. And I want to find out, I'm going to call this location 1. I'm interested in, what is the depth at location 2? This is giving me the slope. It's telling me essentially dy dl, is it saying, if I know that there's some distance between them, maybe it's 100 meters, can I just multiply 100 meters by this and find out how the depth is going to change? What would be the risk of that approach if I was just going to multiply the distance between location 1 and location 2 by this dy dl? Exactly it. So if I did that, if I just said L times S naught minus S sub f divided by 1 minus the Froude number squared, so this is my dy dl, multiply it by L, it's saying, well, just assume that it's a straight line. So you're assuming that it doesn't continue curving, but it does. And so you can't just use this directly to find the new depth downstream. You have to integrate that over the entire distance, because that just tells you the slope at a point. It doesn't tell you necessarily like the average slope between 2 points. But that's one method that we'll take, is instead of doing it here, maybe we'll look at what's the slope there and try and linearize between those two. And sometimes another thing we'll do is we'll break it up into lots of small little pieces, because then that makes the curved slope and the linear slope about the same. So I think you've done things like this in calculus before, where you're trying to find the area under a curve, and so you'll look at the slope of the curve over very small increments, and that tells you essentially, in this case, what the depth is some distance upstream. So that's where we're headed, is we're going to be using this, which tells us what the slope of the water surface looks like, to find the new depth downstream or upstream, as the case may be. So any questions about this slide or where we're headed? Again, I'll emphasize, it's in bold here, that this is just for conditions at one point. You'll calculate at a certain location what is the dy dl. All right, so the S sub f we can find from Manning's equation. We can rearrange Manning's equation and solve for the slope of the energy grade line. The S naught you can measure, or you'll be told in the problem statement what the channel slope is. And the Froude number you can calculate based on the flow conditions. And so if you substitute Manning's equation into this governing equation here, it's called the process equation. If you substitute that in, then here is dy dl in terms of SI and in terms of BG. The difference between them is just that in the BG units, Manning's equation is actually Q equals 1.486 divided by N, A divided by P to the 2/3 power, slope to the 1/2 power. This correction factor is for units in the case of BG units. But in SI, that correction factor isn't there. Now, these are true regardless of what the shape of the section looks like. If it's a trapezoidal channel, if it's triangular, if it is rectangular, that's always true. We do have a simplification if we've got a wide section, a wide channel. Does anybody remember what the criteria for a wide channel is?
20.
That's right, 20. The width should be 20 times the depth. So if you've got a channel that has some depth y, and then the width is 20 y, then we can say that this is wide. And the reason why it's significant is that if you've got a channel that wide, then if it was trapezoidal, it wouldn't be that much different than it being rectangular. In other words, this little area over here doesn't matter much in the scheme of things when you've got a really wide channel where the width is 20 times the depth. So here you can find the slope of the water surface as a function of the normal depth, the critical depth, and then whatever the depth is at that location. So there's 3 different y's that you have to keep track of. Normal depth you get from Manning's equation. Critical depth you get from solving the Froude number. You set Froude number equation equal to 1. The easiest way, if it's a rectangular channel, remember that the critical depth is q squared divided by g to the 1/3 power if it's a rectangular channel. So, and then this y just means whatever the depth is at the point of interest. So remember, this whole equation can only be analyzed at a certain point. And so you'll say, for this point, I know the depth, I can measure it, is some certain y. That's this. And then you can also calculate for the flow conditions that are described, what's the critical depth and what's the normal depth. Substitute those in along with the channel slope, and then you can find out how the water depth is increasing. So the sign of this, dy dl, if it's positive, that means that it's getting deeper in the direction of flow. And if it's negative, then that means it's getting shallower in the direction of flow. So here, what I've drawn is that the depth is decreasing in the direction of flow. And so in this case, what we'd find is that dy dl, if we solved for it, would be negative. But if we had something like an obstruction and the flow depth is increasing as it approaches that obstruction, here you can see that the depth is increasing in the direction of flow, so dy dl would have a positive sign there. Don't use this equation if the channel isn't wide. That's a warning. All right. So this is called the process equation. And I think that's kind of funny, so I put it in quotes there, the process equation. When I heard that, it reminded me of that character from Jersey Shore, you know, the situation, that guy. So this is the process. He's the situation. The sign of it tells you whether the depth is increasing or decreasing in the direction of flow. Here's another thing we can say about a wide channel is that it's a little bit easier than ordinary to solve Manning's equation too. Here's what Manning's equation looks like for a wide channel. You can find the normal depth as a function of the flow per unit width. That's what the lowercase q means, is, remember, lowercase q is q divided by b. So for a very wide channel, we assume that it's rectangular, so that's why you can calculate a flow per unit width. You can't calculate a flow per unit width for a rectangular channel. That doesn't make any sense in the case of a rectangular channel. I'm trapezoidal. Thank you. Yeah, this is a trapezoid.
The process equation is only for wide channels. Is that what you said?
No, we can apply it to channels that aren't wide. It's just that it... Right. Well, remember, we can also find dy dl for just in terms of this. So the simplification is just that Froude number is being, instead of calculating the Froude number at the location, we're using the depths. But the process equation can be applied for non-wide sections. You just have to find the Froude number at the location of interest. But how this is a simplification is because you'll already typically have calculated the critical depth and the normal depth, and then they'll tell you in the problem statement what y is. And so
Always on that next slide.
well, this is the simplification for a wide channel. This is always valid. Yeah. And these are always valid. Yeah. So I maybe should give you the warning on this slide too that this is the wide channel version of it. But most natural streams are wide. Engineered streams, you know, drainage canals sometimes aren't, but a natural earthline channel is ordinarily going to be wide. That's it would be an exception for it not to be. Okay, so let's take a look at an example here. We've got a rectangular channel carrying 20 cubic meters per second of flow. It's 40 meters wide and 2 meters deep. So first of all, what we can see right off the bat is this is a wide channel because the ratio of depth to width is, in this case, exactly 1 to 20, depth to width. So we've got a Q of 20 cubic meters per second. The channel width is 40 meters. The slope of the bed, you definitely need to memorize the three different slopes, S sub W, S sub F, S naught, what those three correspond to. This is the bed slope, the channel itself. The roughness of the material, 0.021 is the end value, and then the depth is 2 meters at some certain location that we're interested in. It's not the depth of 2 meters, it's not 2 meters everywhere. You know, that's what makes this a gradually varying flow problem, is if we went upstream or downstream a little bit, the depth isn't going to be 2 meters any longer. But the place where we're interested in, it is 2 meters. Okay, so a first thing we can do is calculate the flow per unit width, so that's Q divided by B. 20 cubic meters per second divided by 40 meters, it gives us 0.5 meters squared per second as the flow per unit width. And with that, we calculate the critical depth, flow per unit width squared divided by G to the 1/3 power. Okay, the critical depth is 0.2943 meters. And now, since it is a rectangular channel that's wide, we can use the simplified version of Manning's equation to find the normal depth. Q times N divided by S naught to the 1/2 power, all of that to the 3/5 power. Okay, so our flow per unit width is 0.5 meters squared per second. Our N value is 0.021, and the slope 0.00015 to the 1/2 power, and then all of that to the 3/5 power. In these gradually varying flow problems, it's just like the first thing you should do is calculate the critical depth and the normal depth. That's just, if you don't know what else to do, that's a great start. So here we've got both, and calculating the normal depth is 0.912 meters. All right. So now we can substitute it into dy dl. It's S naught 1 minus y sub n divided by y to the 10/3 power, 1 minus y sub c divided by y to the 3rd power. Okay, the channel slope is 0.00015, and then 1 minus, we got the ratio of the normal depth, which is 0.912 meters, divided by the given depth at this location of 2 meters, and all that to the 10/3 power. And then we'll divide that by 1 minus 0.2943 meters divided by 2 meters cubed. This is the kind of calculation I usually triple check because it's easy to make mistakes when you're doing divide to the power, minus, multiply, so many times all at once. So I double check and break it down into steps. 0.00015 times 0.927 divided by 0.997. Okay, ultimately it's 1.39 times 10 to the minus 4th. So this is the rate of flow variation with respect to the channel bottom. So I'm going to write that out longhand just to emphasize what this dy dl actually is. Okay, so okay, now this is not the slope of the water with respect to the horizon. This 0.139 times 10 to the minus 4th is the slope of the water with respect to the channel bottom. So this is the rate of flow depth variation relative to the channel bottom. And so if we're using the channel bottom as a datum, we say the flow is getting deeper or shallower depending on what's happening to this dy dl. And in this case, what we know is that it is going to be getting deeper because it's positive. So the other thing I'm going to write is, since the sign is positive, the flow depth is increasing. Questions with the calculation or interpretation part up till here? To relate the channel bottom? Yeah, yeah. It goes back to here. If we want to know the slope of the water surface relative to horizontal, SW, you would add the channel slope and the water surface slope. So here, if we wanted to know SW, SW would be 0.00015 plus 0.000139. Let's see. 1, 2, 3, 4. Yeah. So what is that? 0.000289 would be the water surface slope. But actually now that I think about it, we have to be careful with the signs because this is positive, but we sometimes just by convention don't bother writing the negative sign in front of a channel slope that's downhill. So actually we'd need to put the negative sign there because that's downhill and this is getting deeper in the direction of flow. So I'd need to find the difference between the two to find the water surface slope with respect to horizontal. Yeah. Because the 0.00015 is downhill. Okay, so like I said, if you sometimes get stuck in a gradual varying flow problem, the first thing to do is calculate the normal depth and the critical depth. And if you're still stuck after doing that, a good thing to do would maybe be to draw a little sketch showing that, the depths that you just calculated. So here, what we calculated was, first of all, there was some critical depth. Y sub c, we found, was 0.2943 meters. So we calculated that, and the normal depth was above that. When we calculated the normal depth, we found that there was some normal depth of 0.912 meters. And then the actual water depth at the location we were interested in, you know, like maybe this was our location of interest, Y was 2.0 meters right here. Okay, so the critical depth continues, the normal depth continues. What you'll see is that sort of breaks our cross-section into 3 zones. 1, 2, and 3. There's the zone above this upper line, in between the 2 lines, and then below the line. What we're going to look at next is how to classify water surface profiles by the relationship between these 3 depths. In our example we just worked, we had Y was greater than Y naught, and Y naught was greater than YC. But that doesn't have to be that case. It could be any combination of depths. It could be that the critical depth is deeper than the normal depth. It could be that the flow depth is in zone 1, 2, or 3. A really important effective thing is to look at, for a problem, where is the flow depth compared to the critical and the normal, and that can sometimes tell you what the behavior will be up and downstream. So let's take a look at some of the things there. There's 3 depths that classify the water surface profile. There's the critical, normal, and then the depth at that location of interest. So what we're going to be going through next is called flow classification, and it's a way of diagnosing the flow regime and breaking it up into categories. And it tells you whether the depth is increasing or decreasing, and sometimes you can get some clues as to why, like what's causing the change, even without seeing it. The first thing we'll look at is the slope. And like I've mentioned before, a mild slope is where the channel bed slope is less than the critical slope. And anytime you have a mild slope, the normal depth will be greater than the critical depth. So what we had in our example just now was a mild slope because the normal depth was 0.91 and the critical depth was 0.29. So this slope is mild, which tells us that the uniform flow should be subcritical anytime there's a mild slope. If it just so happens that the channel slope is steeper than the critical slope, that's steep. And now here you'll notice that it's flipped. In mild, normal depth was greater than critical depth, but here when it's steep, the normal depth is less than the critical depth. That critical depth line is dashed just to sort of show, imaginary where it will be. Now, if it's just a rare coincidence where the channel slope is equal to the critical slope, that's what we call a critical slope or a critical profile. You could have a horizontal profile where there's actually no slope. Or for just a short space, you may even have water flowing uphill in an adverse slope, like at a water park or maybe on a cruise ship where you've seen people surfing on a standing wave. So you could have, over a short duration, water flowing uphill in an adverse slope. So these, M, S, C, H, and A, are the prefix of the water classification process that we're going to go through. And so if it says it's an M profile, then that means the channel slope is mild. If it says it's an S profile, that means the channel is steep. And then you recognize the implications of that with respect to the slope. Now the next part of it is these zones that I've previously alluded to, zones 1, 2, or 3. And regardless of whether the critical slope is on top or the normal, regardless of whether the critical depth is on top or the normal depth is on top, there's still going to be 3 zones. So here you can see it says normal depth or critical depth will be this upper one. Normal depth or critical depth will be the lower one. So it's not going to be critical depth for both of them. It's going to be one or the other on top. And zone 1 is above the highest of the two. Zone 2 is between them. Zone 3 is beneath the lowest of them. So zone 1, zone 2, zone 3. So if you've got a mild slope at a certain location and the actual flow depth is up here in zone 1, like ours was, what we had was an M1 profile for this example. We had an M1 because it's a mild slope. We know it's mild because normal depth is greater than critical depth. And we know it's zone 1 because the water, the actual water depth of 2 meters is greater than either of those other two. So that's what makes it an M1. This just shows you what's happening when you've got positive dy dl, it's getting deeper in the direction of flow. A negative dy dl means that the water depth is decreasing. If dy dl is 0, then that means you've got uniform flow, and then dy dl, if it's negative infinity, that means that there's a free overfall or maybe a wave of water, like in a flash flood situation. Okay, so here is a depiction of M1, M2, and M3. M1 is always getting deeper in the direction of flow, and M2 is always getting shallower in the direction of flow, and M3 is always getting deeper in the direction of flow. M3 is the sort of thing that would be flow under a gate. You still have a mild slope even though you have supercritical flow. So this M3 maybe is because of flow under a gate. M2 might be water that's approaching that overflow, like the waterfall situation. Here is a depiction of an S1, S2, and S3. You can see from the slope of the black line whether it's getting deeper in the direction of flow or shallower in the direction of flow. Here is the S profiles. There is no S2. The reason why there isn't an S2 is that if you have a slope that's equal to the critical slope, then that means that the normal depth and the critical depth are the same. So really, I guess they should have said here, not just YC, they should say YC equals Y naught. In fact, I maybe will add that after class if I remember. So that there's only a zone 1 and a zone 3. And in the case of a horizontal slope, there's no zone 1 because you can have a critical depth, but you can't calculate the normal depth using Manning's equation for something with no slope. Manning's equation is not defined when you don't have any channel slope. And in the case of an adverse slope, the same thing is true. You can still have a critical depth. You can calculate that even if the water's flowing uphill, but there is no normal depth for an adverse slope. So there's no A1 type of a profile. And then here are some depictions of the hydraulic features that can cause these different types of profile. And we've talked about M1 plenty of times before, the types of things that could cause pooling and the water depth increasing. Here's that flow over the edge that causes an M2. And M3 might be where you've got supercritical flow. The depth is increasing even though the flow depth is less than both the normal and the critical depth. Here are some steep slopes. They're a little bit more interesting, the steep slopes, I think, because they're unexpected that you'd see, for example, a hydraulic jump here upstream of the hydraulic feature. Though we talked actually about that in a previous lecture as well. And here are some of the locations where you'd see an A2 or an A3 type slope and critical profiles. And then this is from a different book. This isn't from our text, but I like it just as another summary of bringing it all together, the three different profile types, what it means in terms of dy dx, and what it also means in terms of which one's on top, the normal depth or the critical depth. And here you can see in the case of a mild slope, it's the normal depth on top. In the case of a steep slope, it's the critical depth on top. These are the most two common. I mean, the adverse slope, a critical slope, or a horizontal slope, those don't happen very often. Usually the slope will be either mild or steep. So here are the other three cases. I'll let you look over those. But I'd like you to try out this water surface profile example. You can work with a colleague on this one. The step, first of all, that you need to do is to classify the water surface profile. And so to do that, you need to find the normal depth, the critical depth, and compare it to the depth that's given of 3.2 meters. And so for classify the water surface profile, which is what WSP stands for, first of all, find the normal depth. Then find the critical depth. And compare those two to the given depth y of 3.2 meters. And then the second part of it, find the water surface slope. That is where you're going to need to calculate the Froude number. In this instance, you can, for the water surface slope, you're going to be applying the dy dx is equal to S naught minus SF 1 minus Froude number squared. And remember from previous lectures that what we know about the Froude number squared is it's q squared times t, the top width, g times a cubed. And then you can find the slope of the energy grade line by solving Manning's equation, n times q divided by a, hydraulic radius to the 2/3, and that is squared. All right, so I will turn you loose on that one. Okay, so we'll pick up this example next time, and I'll also let you out 3 minutes early next time since I've kept you a little later. Let's just look at the announcements. Remember that the assignment that's due on Tuesday includes only questions from Chapter 14. So I will see you on Thursday.